Hey, this is Platinum, and this is going to be game theory. And this is going to be theory part 3. So last time we left off with a question, which was, well, how do we maximize EV? So what does this mean? What is this question? So this question is, you fix a game, and today let's talk about where you fix your opponent's strategy. So what this means is that you're going to assume that your opponent doesn't change how they play, and we're going to assume that you know how your opponent plays. And in this context, what strategy can you choose that maximizes your EV? So what strategy of yours maximizes your EV? And so we're going to define a maximally exploitative strategy. So this is a definition of maximally exploitative. I guess we're defining the adjective maximally exploitative. A maximally exploitative strategy which maximizes your EV against a fixed opponent. So this is a maximally exploitative strategy against another strategy. It's against an opponent. You have a maximally exploitative strategy. So for example, the maximally exploitative strategy against Bart's 100% rock is 100% paper, of course. So this wins 100% of the time. So let's talk about this. So here, what's your EV? Your EV is 1, right? You win 100% of the time. If he always throws rock and you always throw paper, you're going to win every single game. So your EV is 1. And of course, you can't win more than 100% of the time, so you can't do better. So that implies this is your maximally exploitative strategy. Maximally exploitative strategy. So I think this is reasonably intuitive. Um, Last time we did an example with Marge, right? Marge throws 2/3 paper, 1/3 scissors. So the maximally exploitative strategy is, turns out in this case, it's 100% scissors. And so last time we gave a strategy that had EV 2/3. Here, your EV is not 1, but your EV is 2/3 plus, oops, plus 1/6. So you're better by 1/6 compared to the what we had last time. And again, if you should be able to calculate this number and come up with it. So how do I know? Well, here's a proposition which helps you with these things. So proposition is a statement of truth that is, of moderate importance. So the maximally exploitative strategy is not always unique. So it's just a maximally exploitative strategy. There may be several ways to maximize your expectation. But there's always a maximally exploitative strategy that is pure. And so how do you know? Well, I invite you to pause the video and think about this for a moment, or you can just listen to me explain it to you. So here's why. So a mixed strategy somehow mixes a mixed strategy mixes pure strategies. So when we say that Maggie plays 1/3, 1/3, 1/3, she's playing 3 pure strategies, each with different probability, right? She's got the pure strategy throw rock, the pure strategy throw paper, and the pure strategy throw scissors. And she allocates probabilities to each of those and plays each of those pure strategies with that probability. So what you do is calculate the expected value of each pure strategy, and then, well, you can just, so if they come out different, if one pure strategy has a higher expectation than another, or against your opponent, then, I mean, throw the better one, right? Don't ever play something that has a worse expected value. So you've got a set of, some subset of the pure strategies are going to have maximal expected value. And now what you do is you just pick one of them. And there you go. There you have you've just constructed a pure strategy that is maximally exploitative. So for example, against Marge's strategy, you calculate, you know what she's doing. She's throwing paper 2/3 of the time, scissors 1/3 of the time. So figure out how well rock does, how well paper does and how well scissors does against your strategy. So for each individual pure strategy, calculate the EV. And so the EV of rock is going to come out to be something pretty bad. Um, the EV of paper is going to come out to be something middling because you're drawing a lot, and the EV of scissors is going to come out to be the thing we just calculated, 2/3 plus 1/6. And then if you were to mix between those strategies, well, I mean, which one are you hoping that random.org generates? You're hoping that it generates scissors every time because that's the one with the highest EV. So just play scissors all the time instead of hoping that random.org generates the right one for you. And so this is a proof of this proposition. And so what that means is that whenever you're trying to maximize the expected value against a specific opponent, so whenever you're trying to find a maximally exploitative strategy against a specific opponent, you just need to check the pure strategies, check them all, figure out which one has the highest EV, and play that 100% of the time, and that pure strategy is going to be a maximally exploitative strategy against your opponent. So at least in this case, where we're fixing the opponent's strategy and the opponent's strategy is known, we can answer our question. We can say, how do we maximize expected value? Well, you check all the pure strategies and just play the one that has the highest expected value, and that'll do it for you. But of course, things get a lot more complicated, and the bulk of the theory is about dealing with situations where either your opponent is allowed to change their strategy or where you don't know your opponent's strategy. And then you've got to figure out how to mitigate this and what to do against it. So that's going to be the bulk of the rest of the theory. But thankfully, we can at least answer this, and it's useful to know about maximum exploitative strategies and know where to start, because ideally, you'd want to play a maximum exploitative strategy all the time if you could, but sometimes that's not possible. But it's important to know what we're aiming for, and that's why maximum exploitative strategies are important.